Hello, dear students! In this lesson, we'll explore sensitive information disclosure, what it is, the risks it creates, real attack scenarios, and the best practices to prevent it. So, here's what we'll be covering in this lesson. We'll begin with an introduction to sensitive information disclosure, where I'll explain why sensitive data matters so much in LLM applications and what kinds of information are at risk. Next, we'll look at the most common vulnerabilities and risks, from personal data leakage to proprietary algorithm exposure and disclosure of business secrets. After that, I'll walk you through several example attack scenarios, showing how these vulnerabilities appear in practice and what impact they can have. Once we've seen the risks in action, we'll move on to prevention and mitigation strategies, exploring techniques such as sanitization, access controls, and privacy-preserving machine learning. Finally, we'll bring everything together with best practices and defensive patterns, where I'll show you how to combine technical safeguards with user education and regular testing. By the end of the lesson, you'll have both a clear understanding of the risks and a practical toolkit of defenses to prevent sensitive information disclosure in real-world systems. So let's begin. When we think about large language models, one of the most pressing concerns is the risk of sensitive information disclosure. This is not a purely theoretical issue. It strikes at the very heart of why organizations, governments, and individuals hesitate to adopt AI systems at scale. Sensitive data is the backbone of digital trust, and if a model mishandles it, the consequences can be severe, ranging from regulatory fines to reputational damage and even harm to individual privacy. But what do we mean by sensitive information in this context? It covers a wide spectrum. At the personal level, it includes personally identifiable information, or PII, such as names, addresses, phone numbers, or social security numbers. At the organizational level, it could be financial details, health records, legal documents, or confidential business strategies. And in the case of proprietary AI systems themselves, even the training methods, source code, or internal algorithms can be considered sensitive assets that must be safeguarded. All of these categories share one common property. If exposed, they create opportunities for misuse, fraud, or competitive disadvantage. The challenge with LLMs is that disclosure does not always happen intentionally. Very often, it occurs unintentionally through the model's outputs. A chatbot might, for instance, generate an answer that includes fragments of another user's data because of poor sanitization. A model connected to a knowledge base might accidentally reveal confidential documents during a query. Or, in the most subtle cases, training data itself may leak through inversion attacks, where attackers reconstruct sensitive inputs from the model's responses. So, as we begin this topic, it is crucial to recognize that sensitive information disclosure in LLMs is not just about hackers extracting secrets, it is also about the inherent risks of deploying models that generate human-like text in environments where privacy and confidentiality are essential. This sets the stage for us to examine vulnerabilities, real-world examples, and the strategies we need to put in place to defend against them. Now that we have introduced the concept of sensitive information disclosure, let us turn our attention to the common vulnerabilities and risks that make this problem so critical. One of the most visible and immediate risks is PII leakage, or the disclosure of personally identifiable information. Imagine interacting with a model and suddenly receiving an output that contains another user's name, email address, or even medical details. This type of leakage not only violates privacy, but can also trigger legal and regulatory consequences under frameworks like GDPR or HIPAA. What makes this especially concerning is that users may not even realize they are exposing their own PII during interactions, and the model may later echo that data back in unintended contexts. Another significant risk involves proprietary algorithm exposure. Large language models, especially those trained on vast datasets, may inadvertently reveal fragments of their training data. If this data includes proprietary code or algorithmic details, the model becomes vulnerable to inversion attacks, methods where adversaries attempt to reconstruct sensitive information based on the outputs. A well-documented case is the so-called proof pudding attack, CVE 2019-2063-4, where disclosed training data allowed attackers to effectively reverse engineer a model's behavior, bypassing security filters in email systems. This example demonstrates that when sensitive data leaks through outputs, the consequences extend far beyond privacy. They can undermine the integrity of entire systems. Finally, we cannot ignore the risk of sensitive business data disclosure. LLMs embedded into enterprise workflows might inadvertently include confidential details in their responses. For instance, a model trained on internal documents could reveal strategic plans, financial projections, or contract details when asked seemingly harmless questions. Even if the disclosure is partial or unintentional, it can hand competitors, attackers, or unauthorized employees access to knowledge that was meant to remain private. Altogether, these vulnerabilities, PII leakage, proprietary algorithm exposure, and disclosure of confidential business data illustrate the range of ways sensitive information can escape through LLMs. They remind us that disclosure is not limited to personal data alone, but encompasses intellectual property, business strategy, and even the models themselves. And this is precisely why mitigating these risks is a top priority in the design and deployment of AI systems. To make these risks more tangible, let us look at a couple of scenarios that illustrate how sensitive information disclosure can happen in practice. The first one is unintentional data exposure, which often occurs because of poor or incomplete sanitization. Imagine a user interacting with a model-based customer support system. Instead of receiving only their own account information, the model, perhaps due to how its memory or context window is managed, inadvertently includes another customer's personal data in its response. This could be something as simple as an email address or as severe as financial or medical details. What is striking here is that no malicious actor is needed. This is purely the result of inadequate safeguards around how the model handles and reuses data. From a compliance perspective, even a single such incident can count as a serious privacy breach. The second case is targeted prompt injection, which introduces a deliberate attacker into the picture. Here, the attacker carefully crafts their input to bypass whatever input filters are in place, instructing the model to reveal information that should remain confidential. For instance, they might trick the model into exposing fragments of training data, system prompts, or internal business records. In this scenario, the attacker leverages weaknesses in the model's trust boundaries, effectively turning the system into a tool for data exfiltration. Unlike unintentional exposure, which is the byproduct of design flaws, prompt injection represents an active exploitation of those flaws. Another important case to examine is data leakage through training data. This usually happens not because of a direct attack, but because of negligence in how training data sets are curated. Imagine a model trained on a mixture of internal company documents and public sources. If sensitive contracts, internal emails, or even personal records are mistakenly included in the training set, those details may resurface later when the model is queried. For example, a user might ask the system about confidential pricing strategies and unexpectedly receive excerpts from a real contract. This type of leakage is particularly concerning because it is baked into the model itself. Once the data is in, it is almost impossible to fully remove it without retraining. Beyond this, there are other practical scenarios we should consider. One is customer support assistants leaking data through contextual memory. If the chatbot is designed to remember past conversations to be more helpful, but it fails to segregate users properly, one customer could receive details that belong to another. This is essentially a memory isolation failure, and it has already been observed in real-world AI deployments. Another scenario involves search-augmented LLMs pulling from unsecured sources. Suppose a company uses retrieval-augmented generation connected to its internal document repository. If the repository contains unclassified sensitive files, say HR records or legal drafts, The model may retrieve and expose those documents when asked a broad or cleverly phrased question. In this case, the vulnerability lies not in the model itself, but in poor access controls around the connected data sources. A further example is API misconfiguration leading to unintended disclosure. Many LLMs are integrated with enterprise APIs, such as those for finance, healthcare, or HR systems. If an API is left open with weak access restrictions, the model could inadvertently surface data that was meant to remain strictly internal. And finally, consider cross-application leakage in multi-tenant systems. If the same model instance is serving multiple clients or departments, and if isolation is not strictly enforced, prompts from one tenant may indirectly influence responses to another. In a corporate context, this could mean a competitor gaining insights into sensitive internal operations simply by querying the shared system. Now that we have seen how easily sensitive information can be exposed through large language models, let us turn to some of the most effective mitigation strategies. The first and perhaps most immediate defense is sanitization. Before any data is used in training or even during runtime interactions, it should be scrubbed, masked, or tokenized to ensure that sensitive details cannot slip through. Scrubbing means removing unnecessary identifiers such as names or account numbers. Masking involves replacing sensitive values with placeholders, for instance, showing only the last 4 digits of a credit card. Tokenization goes a step further by transforming sensitive content into meaningless symbols that the system can still process without ever revealing their underlying value. By applying these methods consistently, we reduce the risk that raw confidential data ever reaches the model in the first place. But sanitization alone is not enough. We also need access controls, guided by the principle of least privilege. This means that both the model and the applications connected to it should only be granted the minimum permissions necessary for their tasks. For example, a support chatbot should not have access to HR records, and an HR assistant should not be able to query financial databases. Similarly, external data sources must be carefully restricted. If we allow the model to pull from every available source without filtering, we are inviting accidental disclosure. Proper access controls serve as a strong boundary, ensuring that sensitive data is only accessible where it is truly needed. There are advanced techniques at the cutting edge of machine learning research, such as federated learning and differential privacy. Federated learning enables us to train models without centralizing all the raw data. Instead, data remains distributed across devices or servers, and only the model updates are shared. This decentralization significantly reduces exposure risks. Alongside it, differential privacy adds a mathematical guarantee. By injecting controlled noise into the training process, it becomes extremely difficult for attackers to reverse engineer or reconstruct individual records from the model. Together, these approaches represent a new direction in privacy-preserving AI, designing systems that remain useful and accurate while minimizing the chance that sensitive information ever leaks. When we speak about protecting against sensitive information disclosure, it is tempting to focus only on technical solutions. Yet in reality, a complete defense must also include human awareness, system-level safeguards, and even advanced cryptographic methods. Let me walk you through these 3 layers. The first is user education and transparency. Many leaks occur not because the system was hacked, but because users simply did not know how to interact safely with a model. People may paste entire contracts, medical histories, or personal identifiers into a chatbot without realizing that this data could later reappear in outputs or even be used for retraining. That is why it is essential to educate users on safe usage, to publish clear guidelines, and to provide opt-out policies for data collection. Transparency around how data is handled, whether it is stored, anonymized, or deleted, builds trust and ensures that users can make informed choices. The second defense is secure system configuration. Even the best trained model can leak sensitive data if the surrounding system is poorly configured. For example, exposing the system's preamble, the hidden instructions that guide the model, can give attackers insight into its internal logic and safety rules. Likewise, misconfigurations, such as verbose error messages or unprotected endpoints, can reveal secrets unintentionally. This is why OWASP emphasizes security misconfiguration as a top risk, even for APIs. Following best practices, concealing sensitive preambles, and ensuring that systems are hardened against these leaks are all critical steps. And finally, there are advanced techniques that push the boundaries of what is possible in secure AI. Homomorphic encryption, for instance, allows computations to be performed on encrypted data, so sensitive content never needs to be exposed in plaintext. Redaction and tokenization techniques can strip or mask confidential terms before they ever reach the model. Pattern matching can automatically detect sensitive information, like credit card numbers or government IDs, and block or transform them before they cause harm. These approaches are still evolving, but they show us that AI security is becoming a highly interdisciplinary field, blending cryptography, machine learning, and classical information security. As we bring together everything we have discussed about sensitive information disclosure, it is important to recognize that no single solution will fully solve the problem. Instead, the most effective approach is a layered one, combining multiple safeguards that address different aspects of the risk. The first layer is technical defense, combining sanitization, access control, and privacy-preserving machine learning. Sanitization ensures that sensitive data is cleaned, masked, or tokenized before it can enter training or inference pipelines. Access control enforces the principle of least privilege so that neither the model nor its connected applications can see more than they absolutely need. And privacy-preserving methods, such as differential privacy or federated learning, provide mathematical assurances that even if data is used for training, it cannot be easily reverse engineered. When these measures work together, they create overlapping protections that are much harder for an attacker to bypass. The second layer is human-centered defense, which comes from establishing clear user-facing guidelines. Users must understand what kind of information is safe to share and what must never be entered into an LLM. Simple warnings, transparent terms of use, and opt-out policies go a long way toward preventing accidental disclosures. By setting expectations clearly, organizations empower users to be an active part of the defense strategy. But even with technical and human safeguards, we cannot assume perfection. That is why the third layer is regular adversarial testing. This involves simulating attacks, both intentional and unintentional, by attempting to extract data or force leaks. Red team exercises and penetration tests help identify weaknesses that are not obvious in normal use. It is a proactive way to discover vulnerabilities before they can be exploited by real attackers. Finally, one of the most effective teaching tools, both for teams and for students like you, is the before and after demonstration. By showing a vulnerable system side by side with a mitigated one, we can see clearly how the same prompt that once caused a leak is now blocked or sanitized. This comparison illustrates not only the importance of defenses, but also their practical impact, turning abstract theory into tangible results. So, best practices for sensitive information disclosure come down to building layers. Robust technical controls, clear communication with users, continuous testing, and visible demonstrations of security improvements. Together, these patterns create systems that are not perfect, but are resilient enough to withstand the risks of operating in the real world. That's all what I plan to discuss with you in this lesson. Let's recap what we've learned today. We learned what sensitive information disclosure is and why it matters in LLM-powered applications. We explored the most common vulnerabilities, including PI leakage, proprietary algorithm exposure, and disclosure of business data. We examined practical attack scenarios that showed how these risks appear in real systems. We reviewed prevention and mitigation strategies such as sanitization, access control, and privacy-preserving techniques. Finally, we discussed best practices and defensive patterns,
combining technical safeguards with user education and regular testing.
That's all for this lesson. Thank you so much for your attention. Have a great day and see you in the next lesson.